Good afternoon, everyone. My name is Giorgos Mellios. I'm the managing director of EMISIA, a member of ALICE. Today I'll be discussing a topic for the adoption of electric heavy-duty trucks, estimating the real-world electric driving range, looking at both data-driven and simulation-based approaches. You can go to the next slide, please. Okay. So let's start with a core challenge. Imagine a typical long-haul scenario, a trip of 800 kilometers. Now consider a pure electric vehicle, pure electric truck with a nominal range of, let's say, 350 kilometers, which looks reasonable. Now, immediately some key questions arise, like how many charging stops are needed, where should they be, what is the optimal charging strategy, charge fully or just enough to reach the next stop, and most importantly, which route is actually feasible and the most energy efficient one. Now, as the graphic illustrates, managing the state of the art becomes important. Dropping below a certain threshold, like 30%, for example, triggers the need for a charge, for a battery charge, impacting the logistics and delivery times. Now, accurately predicting energy consumption and range for specific trips is essential for reliable operations and for overcoming the so-called range anxiety, which is known for passenger cars, but I believe this is also common for heavier vehicles. So this brings us to the main question. How do we determine the real-world energy consumption, and how can we reliably estimate the achievable range for any given journey? Next slide, please. Now, there are fundamentally two main ways to approach this. First, we can estimate range based on measured data. And this typically involves looking at historical data, how far the vehicle has traveled on a full charge in the past, down to a low SOC level, so state of charge level. This data might come mainly from monitoring systems, and soon it can also come from standardized onboard fuel consumption measurement or the FCM systems. The second approach is based on simulation. Here, we use vehicle models to predict or calculate the energy consumption and therefore the range for specific for any specific or any planned trip. And this allows us to account for factors specific to that journey. So we have estimation based on past performance and calculation of prediction based on modeling future performance. Next slide, please. Now, let's take a closer look at the measured data approach. For conventional diesel trucks, we monitor fuel consumed and distance traveled to get fuel consumption in liters per 100 kilometers. For electric vehicles, the principle is similar, but the parameters change. Now, what we need to do is to measure the energy consumed from the battery, typically in kilowatt hours, and the distance covered. And this gives us the real-world energy consumption in kilowatt hours per 100 kilometers. Now, the previous speakers have already explained how to account for different losses across the way, so I am not going to repeat that. So this figure, the energy consumption per 100 kilometers combined with the usable battery capacity gives us an indication of the expected range based on past operation. This relies on having systems on board to accurately record energy usage and mileage. If we can move to the next slide, please. Okay, collecting this real-world data accurately and consistently across fleets can be complex. However, upcoming regulations can simplify this process. So, and more specifically, the OPFCM regulation, which is currently under public consultation to define technical requirements. According to the OPFCM regulation, not just fuel, but also energy consumption and vehicle mass will be recorded. So all vehicles will be required to log lifetime energy consumed, distance traveled, and even payload mass. This standardized data logging and communication will make it much easier to track real-world energy efficiency, as I explained in the previous slide. Now, crucial for range estimation, knowing the energy consumption becomes more straightforward. Furthermore, combining this data with battery durability information, like the state of health, which indicates battery degradation, is expected to significantly increase the accuracy of range estimations over the vehicle lifetime. Next slide, please. Now, let's turn to the simulation approach. This is particularly powerful for predictive planning. As you can see in the workflow, at the bottom of this slide, we start with a vehicle's technical specifications to parameterize a simulation model. Ideally, this model is calibrated using measured data, if available, obviously from the same vehicle that the model has been developed. Then, for a specific planned trip, defined by origin, destination, and payload, we use routing engines to get realistic speed profiles and road gradients for potential routes. This route information feeds into the vehicle simulation model, which calculates the expected energy consumption for that specific trip. Now, the great advantage here is prediction. We can estimate the range for a route before the track even starts. We can also incorporate the impact of factors like ambient temperature, which, as we know, affects battery performance, but also the use of the HVAC system in the cabin of the vehicle, or even different driving styles. Furthermore, this approach easily integrates with tools that optimize routing and charging strategies by simulating multiple scenarios. So it can be considered as an add-on to existing platforms. Next slide, please. A key tool in the simulation landscape, particularly in Europe, is Vector, the vehicle energy consumption calculation tool. Vector has been developed by the European Commission and is already the official tool used for determining CO2 emissions and fuel consumption for new heavy-duty vehicle models entering the EU market. What is important is that Vector's capabilities are being expanded to cover also pure electric and hybrid electric vehicles, and also hydrogen and fuel cell vehicles in the near future. Beyond its regulatory use, Vector allows users to create custom simulations with specific vehicles, loads, and mission profiles. This means that it can be leveraged for the kind of predictive route-specific energy consumption calculations we are discussing in this presentation, helping real-world operational planning. Next slide, please. To summarize the two approaches, on one hand, we have real-world monitoring using measured data that requires different types of recording devices. And this method provides high-quality data reflecting actual usage. Initially, it might need driver input, but standardization via OPFCM will simplify this significantly in the near future. And it primarily gives a historical perspective on range. On the other hand, we have simulation that requires setting up and validating vehicle models. Its strength obviously lies in prediction, estimating range for specific future trips and conditions. And it readily combines with routing engines and allows for sophisticated route and charging optimization before the trip begins. Ultimately, the goal is effective route planning whether using historical data averages or predictive simulation results. The process involves defining the trip, identifying possible routes, calculating the energy needs and achievable rates for those routes, and finally selecting the most efficient option, which might include necessary charging stops. Simulation approaches, especially when integrated with routing engines and charging station databases, offer a powerful way to perform this optimization proactively, ensuring that the trip is feasible and efficient. And that was my last slide. I hope it was within the time allocated to this presentation. Thank you very much for your attention. I'm happy to answer any questions you may have now or later.